Gibbs free energy and the cell potential, we could cast an equation for the cell potential as a function of the reaction quotient, Q. Same way we did with the Gibbs free energy equation, we can find KEQ in terms of the cell potential by setting that thing to zero, setting the cell potential to zero. So at zero cell potential, that's the spot where the cell has stopped moving. It's at equilibrium value. It's pushing with equal force in both directions. We set E cell to zero and do a little manipulation, and we come up with this equation. Natural log of KEQ is VFE over RT. It's equation 9.17 in your book. Obviously then, to obtain the equilibrium constant, you take E to the power of VFE cell over RT. All right? Pretty simple. You guys have probably seen that before. We'll look in a second at some of the effects on this. There's kind of a special form of that equation for a cell that involves hydrogen ion as either a reactant or a product. You can recast that equation in terms of the pH. So you have a direct relationship between the pH of the system and the potential of the cell. Your book outlines an example using the NAD plus H plus goes to NADH reaction, so we're just going to review that real quick. For the sake of just kind of casting the equation, we're going to run some assumptions on this particular cell. We're going to say that, we're going to assume that we've got equal concentrations of NADH and NAD plus. Our cell potential ends up being written out like this. NADH is our product. We take its activity divided by the activities of the reactants. H plus is a reactant in this case, and so is NAD plus. If these guys are equal, then the ratio is just 1, and so we have an equation that says that the potential of this cell is the standard potential minus this correction that has the activity of H plus in the denominator in this case, because that guy was a reactant. We're gonna use a little bit of math here and say that the natural log of anything is natural log of 10 times the log of that item. And so if we're looking at the activity of H plus, natural log of the activity of H plus ends up being natural log of 10 times the log of H plus. So we've switched from using the natural logarithm to an equation that allows us to use the log base 10. We already know that pH is cast in terms of log base 10. It's negative log base 10 to get the concentration of H plus. If we're looking at a dilute cell, we know that activity goes as concentration for a dilute cell. We know that for more concentrated cells, we can't necessarily approximate the activity as the concentration, but in the case that we have a dilute cell, that works. And so this becomes this equation. E of the cell is negative 2.303 RT over F. There's a 2 here simply because in the problem we're using, there's 2 electrons transferred. In general, that's the variable V that your book uses to indicate the number of electrons involved in the process. But we end up with this equation that says that the cell potential is 2.30 RT over F times the pH. So you might be wondering where that came from. pH is a negative log. We had a positive sign here on the correction, but we turned that into a negative sign so that we could use the term pH here. So that's kind of how the sign thing flipped. Let's take a look at that for a second and see what that says. So in this case, H plus was a reactant, right? If H plus is in abundance, do you expect the cell potential to be high or low? Do you expect the reaction to be favorable? So a large positive cell potential indicates a negative delta G, right? We said that. And so if pH is high, that indicates that there's a low concentration of H plus. If pH is low, that indicates that there's a high concentration of H plus. If H plus is a reactant, we expect the reaction to be more favorable with increased concentrations of H plus. With decreased concentrations of H plus, if H plus is a reactant, we expect the reaction to be less favorable. And so you see that negative sign here, the larger the magnitude of the pH, the lower the cell potential is going to be overall, indicating what we just said. Low pH, low pH, high cell potential, indicating large concentration of H plus. High pH, lower cell potential, indicating lower concentration of H plus. Yeah?
Mm-hmm.
And if you had the reverse of this effect where H plus was a product of some particular reaction, then what would happen when you ran through and did this math is that that sign would flip in front of this correction, because now our activity of H plus would be in the numerator, not the denominator. So we'd have a positive correction, and so we'd have the reverse effects if we were looking at H plus as a product of the reaction instead of as a reactant. So we talked about that, or when we first introduced the cells and delta G of the reaction and delta S of the reaction, we said that if you ran the cell, if you discharged the cell through a capacitor, and through the capacitor inside a calorimeter, you figure out that the heat dumped into the calorimeter out of the capacitor was equal to delta G for the reaction. And then we said that if we looked at the solution that actually contained ions, there would be an amount of heat that was released in that solution, and that would be equal to T delta S. So that's one mechanism for determining delta G and delta S for the reaction. You can do it calorimetrically. Run the reactions, figure out how much work you get out of the reaction, possibly by discharging the capacitor through a solution, to figure out delta G, and then the heat that happens, and the other one is delta S. There's also a mathematical way to go about finding delta H and delta S. First of all, for delta G, figure out the cell potential of the reaction under standard state conditions. So throw all the reactants in standard state conditions, measure the cell potential, that gives you delta G. In terms of finding delta H and delta S, there's a method that they use here. They say that if your delta H and your delta S are independent of temperature, we made that assumption a couple of times, then you can take delta G at two different temperatures and subtract delta G at T2 from delta G at T1, or delta G at T1 from delta G at T2. And you end up with an equation that looks like this. The delta H naughts of the reaction cancel because, again, they don't change and they're not multiplied by temperature, but the delta S's, which are both multiplied by temperature in the delta G equation, end up staying in the equation. And so we get a relationship for delta S in terms of the cell potential. Delta S of the reaction is VF times the difference between the cell potential measured at one temperature and the cell potential measured at another temperature. So to figure out delta S for a reaction, you can throw all the reactants in standard state and measure the cell potential at a particular temperature. Run the same reaction at a second temperature and figure out what the cell potential is. And then just simply plug in this equation, VF E of T1 minus E of T2 divided by T1 minus T2 is your delta S for the reaction. Pretty simple. Real quick, just I don't want you guys to think about this for too long, but if you look at the delta G equation, delta G is delta H minus T delta S, and you say, assuming the delta H and delta S are constants, I'm going to take the derivative of delta G with respect to temperature. What do I get? I got this equation right here, delta H minus T delta S, and I'm going to take the derivative of it with respect to temperature. Huh? You get delta S, negative delta S, right? You got the T multiplying the delta S, take the derivative of that with respect to temperature, the T goes away, well, it becomes dt. And you're looking at that. And that's basically what this equation is saying. This delta S is the change in G with respect to the change in temperature. It's dG over dt, right? Here's the change in temperature, T1 minus T2. Here's the change in your delta G of the reaction. VF E of T1 minus VF E of T2. So that's kind of where this equation comes from. To figure out the delta S, we take the differential of, take the derivative of G with respect to temperature. Okay? You look at this math, and there's some implications. So, assuming that you're running an increase in temperature, this term T1 minus T2 is always negative. So that term in the denominator is negative. Denominator? What the? What's it called? Denominator. It's like the Terminator. So basically, what you find out is that if the delta S for the reaction is less than 0, so entropy is increasing or is decreasing in the course of the reaction, then as T increases, the cell potential decreases. If delta S for the reaction is positive, then as you increase T, the cell potential increases. There's something about entropy and temperature. Things that have high changes in entropy tend to be more favorable at larger temperatures. We've seen that a couple times in this course. So if delta S is positive, then delta S is going to be positive. The numerator and the denominator both have to be negative, which means that this term is negative, which means that E of T2 is greater than T1, right? So that's what we saw right there. And if delta S is negative, the inverse effects happen. So that's outlined right there for you. How do we get enthalpy? We've already got delta G. You got delta G just by measuring the cell potential. And you figured out delta S by taking the derivative of G with respect to T. And then you just plug them in. Just plug in the value that you calculated for delta G. So you take your delta G as delta H minus T delta S equation, and you rearrange it. Delta H is delta G plus T delta S. Plug in your determined values at your temperature, and that gives you the delta H of the reaction. So in that other calorimetric version of this thing that we looked at, where we said, I think it was zinc ion and silver ion or something like that reacting, we figure out delta H by just simply measuring the heat, the total amount of heat that was dumped out into the calorimeters. That heat, when we just mixed the reactions together, was like 233 kilojoules, and that was the total value for delta H. So you can do this calorimetrically, or you can do some math. Okay, so now we're getting into chapter 10 material. I believe this is chapter 10 material. Unless it's chapter 9, I just can't count. Maybe it's 10 and 11. 10 is the first piece on kinetics, and then 11 is the second piece. We're going to start talking about rates of reactions. You guys are probably pretty good with this stuff by now. It seems like most of you get a lot of experience with this. A reaction rate, you know, is the rate of change of concentration with respect to time in a reaction mixture. And, you know, depending on whether we're looking at, we want to define rates as positive, total rates as positive, then we have to consider whether or not we're looking at a reactant or a product. If we're looking at a reactant, we multiply its rate by a negative sign to make the overall rate positive, since the rate of change is negative. For a product, the rate doesn't have to be multiplied by anything. It's always positive. In order to monitor concentration, we have to have mechanisms for quantifying how much material we have, and there are many mechanisms available. Your book mentions a few. Spectroscopy in general, spectroscopy is a big broad term. There are a million different kind of atomic properties that you can monitor with light. You can monitor absorption and emission. You can go through a big range of wavelengths. UV-Vis monitors electronic transitions. So you can look at the excitation or the de-excitation of electrons, and if you know what the particular values are for your species, then you can figure out its quantity. So if you have a molar extinction coefficient. I was going to derive Beer's law for you, but I don't think I'm going to have the time. Have you guys ever gone through that derivation?
Yep.
Beer's law derivation? Basically, you just take an image where you say you've got a solution, and your solution has a number of absorbers in it. And Beer's law only works for dilute solutions. You calculate, or you know what your incoming intensity is of light, and you look at what your outgoing intensity is, and you run the assumption that every photon that passes through has a chance to hit an absorber. And as long as concentration is low enough that there aren't any, that you can assume that there aren't any molecules hiding behind other molecules that don't. So if I've got incident light here, incident radiation, and this molecule is hiding behind this one, then this guy effectively blocks this one from ever having a chance to absorb light. And so Beer's law doesn't work for this kind of situation. It only works for dilute solutions when you can assume that there's nothing blocking any of the species. In that case, there's a natural log dependence of the decrease in the intensity of light with respect to the distance traveled through the solution. And you end up with this Beer's law equation. The absorbance is log of the initial, or I naught over I, which is equal to the extinction coefficient times the path length times concentration. So Beer's law you use for spectroscopy. You can, for reactions that create ions, you can look at conductivity. For the reaction that changes the optical properties of the solution, you can look at the polarimetry. There's a million different ways to monitor species. Did I already say titration? You can titrate a reaction with some other reactive chemical, and if you know the stoichiometric relationship between the titrant and the titrated molecule, and you can determine what the concentration is by titration. So monitoring concentrations, spectroscopy, conductivity, you look at pH, you can titrate it with some reactive species, and there's others. Your book talks about stop flow techniques and flow techniques. It's just basically different mechanisms for sampling the product or sampling the reaction or the reaction solution at different time intervals. So you just let the reaction run and look at the concentration. and that'll tell you what the rate's going to be. So we're just going to be looking at some really basic rate mechanisms today. Next week we'll start to get into some more complicated stuff. A lot of times the rate laws end up being very simplistic, and you have something that says that the velocity is equal to some constant k times the concentrations of reactants raised to a power. For mechanisms that involve a back reaction, for mechanisms where there's an equilibrium, then the concentrations of the products will also be involved in the rate constant, and so you won't have necessarily this simple relationship. But that said, oftentimes you can push the reaction, or put the reaction in a position where you get very simple rate laws. And sometimes you don't have to do anything. Sometimes the rate law just comes out simple. K is your rate constant. We're going to find out that the rate constant is a function of really the reaction coordinate. So it's a function of temperature. You know, we'll talk about rates, and we'll say that reactions rely on collisions. Two species have to collide in order to react, and so as temperature increases, the number of collisions increases, and so the rate increases, and so your rate constant ends up being dependent on temperature. But also, simply having a collision between two species is not necessarily enough. The collision has to happen in the appropriate orientation. So you can imagine if you've got like a SN1 or an SN2 reaction, and the collision happens from the wrong side. You know, you've got a backside attack, but you collide from the front side, you're not going to get a reaction, right? And so the rate that a reaction proceeds at depends on the specific requirements in order for a collision to result in reactions. And so we'll find out that K accounts for that. Accounts for the collision dependence on reactivity. Talk about reaction orders. Don't think I'm done talking to you guys about this stuff, because I'm sure you've heard it all before. We've got first order reactions, second order reactions. We have reactions that are not integral orders. So a first order reaction is a reaction where you can describe the velocity of the reaction as K times the concentration of a reactant. We'll find out that you can make pseudo first order reactions. A second order reaction is where you have, generally it's because you have a collision between two species required for the thing, but it's not necessarily always the true. Second order reaction is where you have concentrations of two items that govern the rate law. If an A and a B molecule, if the rate is dependent on the concentration of A and B, then it's first order in A, it's first order in B, and it's second order overall. You can also have reactions that go as concentration of one items to the second power. And so if a rate law looks like this, K times conc A squared, then it's second order in A, it's second order in, or second order overall. They don't necessarily have to have integral orders, we just said this. So this reaction is half order in A, it's first order in B, and it's 3/2 order overall. I wrote second overall, that was wrong. It should have been 3/2 order overall. This reaction is an example of what the rate law ends up looking like when you have a back reaction. When you can't say that the reaction goes only to products, the products go back to reactants. In that case, you have terms that look like this, where in the denominator you'll have a K for the back reaction times the concentration of a product. This reaction is first order in H2. It's got concentration of Br in the numerator and the denominator, so they say that it's indefinite. The order is indefinite in the concentration of bromine, and it's also indefinite in HBr. So we don't always have simple rate the laws. Sometimes we do, and we're going to look at a few situations, there are a few things that we can do, a few manipulations we can do when we do have simple rate laws. It's hard to predict what the rate law is going to be. Lots of reactions proceed through different specific steps in different stages, and it's those stages, it's the nature of those stages that ends up determining the rate law. This is actually a pretty interesting example to demonstrate that it's not always easy to predict what a rate law is going to look like. We've got two reactions that seem like they should be equivalent almost. We've got halogen gases reacting with hydrogen gases. Bromine iodine, same octet configuration, single bond between those guys, reacting with H2. If you didn't know any better, you'd expect that they have the same rate law. It turns out that the hydrogen iodine reaction ends up having a very simple rate law. It just ends up being proportional concentrations of hydrogen and iodine raised to the first power. But then you look at the rate law for the bromine reaction, and you can see that it's not simple at all. You've got some kind of a term for a back reaction. There's some equilibrium being established, and so the rate law for that bromine guy ends up being complicated relative to the rate law for iodine. So we'll get into rate determining steps and back reactions and all that stuff next week. But just take home message, rate laws have to be determined experimentally. You can't simply just look at the reactants and products in a reaction and figure out what the rate law is going to look like. There's a technique called the isolation method. You use it a lot when you want to kind of get rid of the effects of other components in a reaction. So say we want to look at the effects of the effects on the rate with changing concentrations of species A. In that case, what we would do is we make the relative concentrations of A and B way disproportionate. We raise the concentration of B to excess so that as the reaction proceeds, it's effectively constant. In that case, your concentration of B can be absorbed into your rate constant, right? Because if B is a constant and this is a constant, this is a constant, they converge into a K effective, an effective rate constant. And so then you have a rate law that ends up being first order in A instead of a rate law that ends up being first order in A, second order in B, third order overall. Okay? Do the same thing with A. If you raise the concentration of A to excess, then you have an effective rate law that goes as the concentration of B squared. This is called creating a pseudo-order rate law. This is a log-log plot. For a log-log plot, you take the logarithm of the rate, and you take the, you write your rate expression, you take the log of both sides. And what you end up finding out is that a log plot will pull out the exponential factor in front of, or the exponential factor to the concentration. So we know the reactions can be first, second, third, whatever order in a reactant. You take the log of it, that log comes down and it becomes a multiplier. You've got log of the velocity, log of K, K is a constant, velocity is